Sure.
Go.
Okay. So, hello everyone. Today we have Ryan Thorngren, who will tell us about the symmetry breaking long exact sequence. Over to you, Ryan.
Okay, thank you. Yeah, thanks for inviting me to give the seminar. It's a pleasure to tell you about this work. So this work, the history is in a few years ago, Zohar Komogradsky, Itamar Hassan, and I worked out that if you want to study anomaly matching for defects, which I will recap for you, there's this Smith homomorphism. But at the time, we didn't understand the kernel and the co-kernel of this map. And then a couple of years ago, this group of young mathematicians came to me. So Arun is a postdoc at Purdue. The rest of them are graduate students at Harvard and MIT. And they came to me and they said, "Oh, we solved your problem." I was like, "Oh, great. Let me see the answer." And they showed me an answer that has so much beautiful structure and contains the answer to so many other anomaly matching questions I was interested in, and it fits them all together into this long exact sequence. So I'm really excited about it, and I'm happy to tell you what we did. So I just interpreted what they did. Okay, so I'll give you my interpretation. So we're interested in let's say, let's pick up here. Okay, good. Yeah, we're interested in defects in symmetry breaking states. So, for example, if you have Ising type symmetry breaking, you have Z2 symmetry is broken down to a trivial symmetry group, then you can think about domain walls where the order parameter, let's say phi, takes one value, one of its vacuum values, and another domain where it takes the opposite vacuum value, transformed by the symmetry. There's some kind of defect between these, which is protected by the system being in one of its two vacua on either side. Okay, similarly, if you have XY type symmetry breaking, it's like an XY ferromagnet of some kind. You have a U1, like a spin rotation symmetry in the plane that's broken down to nothing. And here you have codimension 2 sort of defect. You have vortices. So you have points where you can think about the order parameter, the argument of the order parameter winds around the vortex. But here we have a domain wall, here we have vortex. The general sorts of defects that I'm going to be interested in are going to be, so we have our symmetry group G, which for me will be the symmetry which acts on the bosonic observables of the theory. And we'll have a orthogonal, like a real orthogonal representation, which for this talk will be called V, which will be of dimension K. So I'm thinking about V as the space of the order parameters. So they're Hermitian observable, so they have a real structure. So this is going to have naturally a orthogonal representation. So for instance, in this Z2 case, here V is like the sign representation, the order parameter transforms in the sign. Here V is the charge 1, or yeah, it's the I'll call it the charge 1 real doublet. If you diagonalize it, they would be charge plus minus 1, right? But it's a real representation. K equals 2. Yeah, it's charge 1 real doublet of U1. Okay. Then
how does this fit when you have a G is S3 and then you take some, or even Zn, and you can have a You can have representations of Zn which are not real, in which you have phases.
Yeah, but I always want real representations to when you act on order like observables. Like you might say that, oh, I have observable, it has charge 1 under Z mod n, a complex charge, but then you just take real and imaginary part, and then you get the sort of representation I'm talking about.
I see. Okay, thanks.
Yeah, no problem. Yes, good question. So yeah, this will be the data, and then the defects are going to be defined as follows. So I'm going to say a V defect. Roughly speaking, it's a defect where the order parameter winds around 0 in this representation space V. So it winds around the sphere V. And I'm going to look at actually a specific V defect. So the V defect I'm going to be interested in is actually given by explicit symmetry breaking. So you can think about these results, they'll apply to spontaneous symmetry breaking, but let me just explicitly break the symmetry in my system and define a V defect by a symmetry breaking field. So by a by spatially varying symmetry breaking field, which I'll call phi. And so phi will be a function from our spacetime Rd to V, our vector space is k-dimensional. I'm going to split this Rd into Rk times Rd minus k. So we're going to have coordinates x on Rk and y on Rd minus k. And I'm going to define phi of x and y. It'll actually only depend on x. So it'll be the sum I equals 1 to k of phi I times xi, where phi I is a basis of V. So I'll give you an example in a second. But so roughly speaking, in terms of the domain wall, we're imagining doing something like applying a magnetic field to the system, which looks like X. So it's forcing there to be a domain wall at the origin. Here we're, in the XY case, we're also applying something like a magnetic field, but it's like a radial vector field. It's forcing there to be a vortex at the origin. So this is going to allow us to probe these defects.
Hey, Ryan.
Yeah.
I mean, I think there are some patterns of symmetry breaking that don't correspond to just representations on a vector space. Like, is that really important for what you're going to say?
I'm going to be considering this. So like well, I mean, there are embedding theorems for homogeneous spaces that you can use. But the only thing that's really different between this and say the G mod H story is that in general, this V, like its various spheres, which are the things that are acted upon, are unions of orbits rather than single orbits.
Yeah, I was going to ask a related question. Here, G is broken completely rather than broken through a subgroup H. And second,
no, it's not necessarily broken completely. Not at all.
Okay, but so far H, the unbroken subgroup, hasn't appeared in your data. And the second thing is that K is less than capital D, which again seems a little bit restrictive.
Yeah, we need K less than capital D. I mean, these are all important things that you'll see. But okay, I'll give you another example. So let's take G to be SO3 and V to be the vector rep. This is another example. So here you like the symmetry is broken down to some SO2. And there's a codimension 3 defect associated with this, which is the hedgehog. Okay, so these are the defects I'm going to study. So we're interested in localized modes on the defect. So to give you example of what I'm thinking about, let's think about the 2+1D, the 2+1D Majorana fermion.
So in the case of Zn spontaneous symmetry breaking, are you looking at codimension 2 defects?
It depends on the representation you choose.
Yeah,
I'll do
let's
many.
say let's say
You
the
can choose a group
representation.
and a representation in this game.
Yeah, so let's take the representation to be the one which is the generator of the Pontryagin dual group.
Okay.
So just the nth root of unity. So this is a two-dimensional real representation, but the only defects that are natural are codimension 1.
No, you have codimension 2 defects. You essentially have the U1 case here, but then you've also broken the U1 down to Zn.
I mean Zn
Like
breaking to
pictures
1.
where, oops, you get pictures where you have a domain walls meeting, this sort of thing.
I see. Okay.
This is all allowed.
Okay. I see. Okay, thanks.
Yeah, we just need this linear structure. You'll see why we need it. Okay, but let me do an example. So let's think about this two-component real fermion in 2+1 dimensions, and I'll do this one in some detail just so that you have something concrete to think about. So yeah, the real you can have a two-component real spinner in 2+1 dimensions if you like the Pauli matrices you can choose in terms of the gamma matrices you can choose in terms of the Pauli sigma matrices, or like so. So these are all 2x2 real matrices, and they give you a representation of sign 2-1. So signature minus plus plus here. And we're going to consider G to be Z2. We're going to take it to be time reversal, which acts on the fermion, has this gamma matrix that you need for it to preserve the kinetic term, and then it reverses the direction of time. And now this theory, you can write a mass term for this Majorana. So it looks like this. Now, you need the I in mass term for this operator to be Hermitian. Because if you think about taking its Hermitian conjugate, so I just wrote transpose because everybody's real. So we just transpose the contraction here. So the size swap, but the transpose comes along, so you don't have to swap them anymore. And then gamma t gets transposed, and gamma t is an antisymmetric matrix. So you get a minus sign. And in order to fix that minus sign, you have to have an I in front if you want the mass to be real. So this I is there for hermiticity reasons. And when you have it, it makes this be T odd. So this is breaking, if you add this term, you break the time reversal symmetry of the system. You can check that, well, there's some gamma t's that come out in the transformations, but you should check that you get an odd number of minus signs. And so this is going to be the operator we're going to think about as defining some kind of V defect. So we're going to think about, so for us, V is going to be the sign representation that this operator transforms under. So we're going to think about the V defect. So that's like taking mass to depend on X. There'll just be some coordinate X. So it's not going to vary in the Y or the T coordinate. And now if you solve the Dirac equation, now I'll just say sort of schematically what you do. So you want to write your spinner as, it's a function of X, Y, and T. You want to write it want to do separation of variables. So you want to write it as a function of x times the spinner eta in the y and t part. And then if you look at the Dirac equation, it splits into two equations. So one equation, so let me just write it. So you have gamma x dx f of x plus m of x f of x times eta plus gamma y dy eta plus gamma t dt eta times f of x is 0. So this is a Dirac equation once you do the separation of variables. So you get two independent equations. And well, these equations are sort of annoying because of this gamma x matrix in the first one. So the idea is to diagonalize gamma x in the eta. So we're going to look at eta plus minus, which is eigenvalue under gamma x. Gamma x's eigenvalue is plus or minus 1. Cool. So with this choice of eigenvalue, you can solve the first equation in the brackets there and find that f of x is essentially some constant times integral minus plus, where here's the eigenvalue. So let's call it f plus minus integral 0 to x of m of x tilde dx tilde. Okay, so for m of x, for m of x equals x, this guy is some constant times e to the minus plus half x squared. So there's a problem if you have the wrong sign here. So if you choose gamma x to have a minus eigenvalue, then this is not a decaying function, right? It's growing exponentially fast, and it's not giving a good solution to the Dirac equation. So we need to pick the other sign. So you need gamma x eta. You need to take the plus sign, in which case it has Gaussian decay. And with that plus sign, you can look at the other equation. So the one for eta, given this plus sign, well, now that we've diagonalized gamma x, we have to deal with the fact that there are gamma matrices in the eta equation, but there's a way to deal with that, which is that you multiply through by gamma t, and then it becomes gamma t, gamma y, dy eta minus when you get gamma t squared. You get this equation, but now gamma t, gamma y is gamma x. I'm not being too careful with signs here. You can work out the signs if you really want to. So remember this, we chose eta to be an eigenvector. So what we're getting is this equation. Or one component of the eta. So we have one real component satisfying this equation. So this is a chiral Majorana. So the situation we have, I'll draw it again. So I'll draw the full space picture. So we have some region where m is positive, some region where m is negative, and along the domain wall we have a chiral fermion. So these are the sorts of modes we're interested in. This is an anomalous mode because it's chiral. So it has chiral gravitational anomaly. And we want to advocate the point that this mode, well, this mode is anomalous. The original theory also was anomalous. So oops, stop doing that. what I'll start calling the bulk theory is, so this has chiral anomaly. And this has parity anomaly of the symmetry T. And the question is, how do they match? So this is the basic defect anomaly matching question. You have some anomalous symmetry, you break the symmetry. On the V defect, you get some anomalous modes. How are the anomalies related?
I have a quick question. So the mode also has a time reversal symmetry with an anomaly, right?
Mhm.
That is not going to play any role here. Like it's completely.
No, that's exactly the point. So the question is, how does
okay.
the time reversal anomaly match the chiral anomaly on the domain wall?
Well, sorry, the mode has two symmetries, like unitary and anti-unitary, right?
This mode is just some chiral mode so far.
Right, but the 1+1 dimensional reduction, that one has two symmetries, right?
What symmetries does it have? It's just a chiral mode.
Yes, but it's a 1+1 dimensional mode, right? You
Yes.
can think of, take the effective theory of the mode, like a 1+1 dimensional theory.
Right. It has a gravitational anomaly, which is going to match the time reversal anomaly. I'll tell you what other symmetries it has as well.
The question is that this mode has multiple symmetries. I'm trying to see which one is the one that plays the role. It's going to be important here. So you have
I'll explain that. Don't worry. I'll get there. Okay. So, but I'll get to it. So, right. We're just asking at this moment, how do the anomalies match? So the tool we have available to us is anomaly inflow. In other words, we have a correspondence. We have a bulk boundary correspondence. Between anomalies and invertible TQFTs. So I'll call them ITQFTs. So the physical picture of what we're doing is, so this mode that this 2+1D Majorana fermion, in condensed matter physics, it naturally lives at the boundary of this 3D topological superconductor. So this 3+1D topological superconductor that has ordinary time reversal symmetry and no interesting local degrees of freedom of its own. And then you have the 2+1D Majorana on its boundary. And what we're going to do is we're going to extend the V defect to the bulk. And when you do this, so for instance, here's our domain wall with its chiral mode, where we broke time reversal by having positive mass, say, above the domain wall, negative mass below the domain wall. Maybe I should have drawn it vertically. Anyway, if you think about adding an extra coordinate to the V defect, it's still the V defect, right? So you're just adding to the Y coordinates that the profile doesn't depend on. So this, if you extend the time reversal breaking to the bulk, you get a V defect in the bulk. And evidently, there's going to be some invertible TQFT on the V defect of the bulk, which is going to control the chiral anomaly. So for this 3+1D topological superconductor, if you go through the exercise, you'll find stop doing it. You'll find a P plus IP superconductor on this domain wall, which sort of explains the existence of the chiral Majorana there. So of course, these are all known facts about topological superconductor, but I'm just going to put them into some kind of framework. And so in order to do this, all you really need to know about invertible TQFTs is that, for the purposes of this talk, we'll say these are determined determined by a partition function. Actually, let's write it here. So an ITQFT will be the same data as some partition function evaluated, and something's called
There's
Z.
a question in the chat,
Now,
but
one
you
second.
can unmute yourself, Yanis, if you can ask.
1 second. Let me just finish this. So the invertible TQFT will be determined by a partition function, which takes values on closed big D dimensional space times. They'll be equipped with, say, a G gauge field. And some kind of structure, some kind of G twisted tangent structure, such as a spin structure. And these are elements, these these are basically just complex phases. So they're norm 1, and so they form a group. You can multiply them. And I will just say that let's just define this group, just some notation for such functions, which I'll tell you a bit of their properties, but the functions will have they're associated with a group, structure type S, which is typically like spin or SO or something, and then some kind of twist, which is given by a vector bundle. It's given by a representation of G. So that's just some notation. So we're going to be manipulating these objects. Okay, now I can answer your question.
No, I was just curious where at what part of the domain wall is the mass positive and which negative? I missed that.
For which, well, here we chose a mass that was just equal to X, right? The simplest math profile that you can have. So it's, X, M, it's like this. It's positive on one side, negative on the other side.
And then on the domain wall where you have the chiral mode, did you specify which part of the domain wall is the mass is positive and which is negative?
Yes, of course. So we did it for a specific mass. If you do it for the other mass, you'll see that the other mode is the one that becomes normalizable, and so you get a mode of the other chirality.
Okay, I see.
Mm-hmm. So yeah, it's some exercise. I mean, this is like very old Jakiv and Rebbe kind of stuff. Okay, cool. So what we're going to do is, so we need some way to, we said we need to extend the V defect into the bulk. So we need some way to define, or we want to define, the V defect in X. So what we will do, so previously we chose our map phi in a very special way. Here we're going to be a bit more flexible. We're going to choose a section of a certain bundle. So let's let PA be the gauge bundle for A. And let's consider this associated bundle. We use the action of G on our vector space to create a vector bundle. This will be some bundle over XD. And we're going to choose a section phi of this bundle. What you can think about is, if the gauge field is trivial, this is just a map to V. So this is like our symmetry breaking field chosen over the spacetime. But if we want to turn on a gauge field, we have to appreciate the fact that G acts on this vector bundle. And so the right thing to do is to have phi not be just a continuous function to v, but for it to glue according to the transition functions of the gauge bundle, and you track through like what that is, and that's just a section of this bundle. And with this choice of section, the v defect is this set where phi vanishes. And if you look at a generic section locally near this defect, it looks exactly like the v defect that we were considering, where you just have linear dependence, right? So, and also this will be a manifold of dimension t minus k. And we're going to think about it as this is the space-time. This is the space-time for the v defect. And so essentially, let's make an assumption. So assume where phi is non-zero, the bulk invertible topological field theory is trivializable. So we broke the symmetry. I'll say more about what this assumption means, but we broke the symmetry. We want to make sure that the bulk theory really becomes this theory really becomes trivial, not just an invertible theory, but a real trivial theory. Then, or in other words, you could say this is about the same thing. Then this partition function can be evaluated. You know, it gets trivial contribution away from the defect, so evidently it can just be computed along y, and so that will define the defect partition function on this y and whatever structure we have on y. So we have the gauge field restricted to y, and we have the rest of the structure restricted to y.
Excuse me, I have a quick question.
Yeah.
So K is the dimension of V, and V was something that we chose in the very beginning, and it's fixed. So I guess I'm just confused because it seems like all the defects we have will be of the same dimension, and it's not allowing to have defects of different dimensions at the same time. So am I
you can have
missing
different
something,
V's, of
or am I
course,
confused?
right?
But I
You can
thought we
choose-
kind
you can
of fixed
choose
V
G.
in the beginning of the game.
Yeah. For every G and every V, we can study some. I'm studying a particular defect, right?
I see.
Every kind of defect will have its own defect anomaly matching problem that you can study.
I see. So, for instance, with the G equals SO3 and V being the vector rep, you said that was like SO3 breaking down to SO2, and you said there was the hedgehogs.
Right.
But if I'm thinking of it from like the G mod H picture, then I could also have the higher codimension defects as well. So that would be choosing a different V. It wouldn't be the vector rep. Is that right?
Well, you have to be careful. I mean, not all of these will have good anomaly matching problems. So these are the ones that are good, is these particular V defects.
I see.
We should talk about it later.
Okay, so oh, yeah, for sure. Okay, thanks.
Okay, so essentially this equation gives us a way of, if we know what the anomaly on the defect is, we can compute the bulk defect anomaly. The bulk anomaly, which is maybe not the way you thought it would go. Maybe the way that I would have thought, perhaps, is that if you have the anomalous theory, it tells you what the anomaly on the defect is, but it's actually the other way. So what we're getting is a map from defect anomalies to bulk anomalies. In terms of the omega, what we have on the defect, some D minus K dimensional theory. And what sort of structure does it have? Well, it has this G gauge field, so it has some kind of G structure. It has some kind of S structure, psi, that's restricted to it. But when you do this restriction, you have to keep track of the normal bundle. So the twisting bundle of that structure, and this is a technical point, don't worry if you don't get it right away, that the twisting bundle is twisted by the normal bundle of the defect, which in this case is V. So we're getting a map like this. And this was this map that we previously called the Smith map, and we didn't know its kernel and the co-kernel. So hopefully I'll be able to explain the solution to that problem. But first of all, there's an immediate question, which is, what is the interpretation of the gauge field restricted to Y? So this is a G gauge field. It only really makes sense to have a G gauge field in the partition function if you have some G global symmetry, but we broke the symmetry to create the V defect. But the idea is that we broke it in a very special way. So although G is broken, we actually preserve some isomorphic copy of G, which we can call GV, which is embedded in G times rotations and reflections around the defect, right? Because of this linear form, if you act by G on the defect, it just, say, a orthogonal representation, like special orthogonal representation, then just rotates the profile. So you can compensate the action of G by rotation. So if we have Lorentz invariant theory, we're happy. So let's just think about Lorentz invariant continuum theories here. And also, if we have Lorentz invariance, then we have one other orientation reversing symmetry, which we can use in the case of things like the Z2 case, where it flips the orientation, which side the mass is positive, right? So there's going to be some embedded copy where we have SOD, semi-direct, this extra symmetry that we have, which I'm going to call CRT. So it's because of the CPT theorem that we have such a symmetry. So it's essentially, it reverses time and it reverses the direction of space, and it does something else on the internal degrees of freedom. And it's an unbreakable symmetry. It's part of the Lorentz group. Unbreakable as long as you're going to preserve Lorentz symmetry. So when we have, what's going on here is, when we have, say, the time reversal breaking, so back to our example, T breaking in 2 + 1D, so we had this domain wall where the mass is positive on one side and the mass is negative on the other side. Time reversal symmetry can't act on the domain wall degrees of freedom because it doesn't preserve the boundary conditions, right? It negates this mass. But if you combine time reversal with this CRT symmetry that reflects the profile, then everything is good. And well, you may worry, okay, CRT also contains time reversal, but the mass term, right, psi bar psi, is Lorentz invariant. So in particular, it's CRT invariant. So if you look at CRT, so reflecting in the x direction, it's also CRXT times T applied to M of X, you get the same profile again. And if you look at what it does on the fermion, the same thing. Oops. If you act by the same thing on the fermion, X, Y, T, you get so you're gonna from CRT you get a gamma X, gamma T, and then from T you get another gamma T. So the result is gamma X. We reverse the X coordinate, and we reverse the T coordinate. And notice, by the way, this unitary symmetry. So we have we started with an anti-unitary symmetry, which is broken. We get a unitary symmetry on the domain wall. And also notice that gamma x, remember gamma x, what symmetry was this on the degrees of freedom? So gamma x was, this was the chirality of the domain wall mode. So what we're getting, the symmetry we're getting on the wall, so we get this Z2 chiral symmetry. On the domain wall. Okay, so we're ready to compute this defect anomaly map. So where's this map? What's this map supposed to do? So it's supposed to go from the anomaly on the wall to the anomaly in the bulk. The anomaly on the wall is given by omega 3. Remember, it's a 3D space-time that this 1 plus 1D thing lives on the boundary of. It has Z2 symmetry with spin structure and no twist. So it turns out this symmetry, this is just unitary Z2 symmetry, just squares to 1. And if you compute what this group is, it has 2 parts. There's a Z8, which you can think of as the number of charged, Z2 charged left movers minus the number of Z2 charged right movers. And then there's a Z part, which is the gravitational part, which is just the number of left movers minus the number of right movers. And this thing is supposed to map to the anomaly, to the parity anomaly, which, if you write it in all of the details, is a Z2 spin with a 3 times the sign representation twist. Or more succinctly, this is pin plus, which is a Z16 group. So what is this map? Well, we computed one instance of this map. For this mass profile, we found one left mover, which was neutral. So we found one neutral left mover. So that corresponds to 0, 1 in this first group. And well, they both it corresponds to 1 in the Z mod 16. So evidently this map is taking 0, 1 to 1. Now, if we took the other mass profile, m equals minus x, we would find one charged right mover. Right? We would get an opposite chirality, but now gamma x would act with the other sign. So you get one charged right mover. So here, just make sure that I follow the same convention. We're going to get minus 1, mapping to 1. And now this defect map is a linear map. So we actually computed it entirely. So putting these together, you get that this defect map for A comma B, what should it be? I think it should be A minus 2B. Or, sorry, other way around. So B being the gravitational part. So B minus 2A. So this is the formula for how to match the anomaly. So in general, with these defect anomaly maps, they're helpful in various ways. Like it can be very difficult to, if you have some theory that's not a free fermion, has some time reversal symmetry, you want to know its anomaly. It can be very difficult to compute the Z16, right? You don't want to think about putting the theory on RP4 or something like that. That's going to be a headache. Much rather break the symmetry and reduce the dimension. And then with some well-chosen examples, some free fermion examples, you could just compute what these maps are and use the formula to reconstruct the anomaly that you're interested in. It's quite useful. But beyond that, the question is, what are the kernel and co-kernel of this map? Or let's say image of the defect anomaly. So the image, these are going to be bulk anomalies where we can apply this defect anomaly matching, where we can actually do this dimensional reduction. So the image are those anomalies compatible with the existence of a local V defect. So there's a way to think about the obstruction to this existence as a kind of family anomaly. So let's think about, so the question, so so let SV be a large sphere in V. And then for each V in this sphere, we want the anomalous theory with symmetry broken by V. In other words, you add the operator in the direction of V with that magnitude. We want it to have a unique gap ground state. Because when you form the V defect, we want to study a local theory to associate anomaly to it. So we want the theory out here, we want all of this to be a trivial theory. Right? That's what we need to have a local defect. And so it turns out there's a solution to this problem where so given our invertible TQFT, we get a family of invertible TQFTs over the sphere by breaking their symmetry. And in fact, we get a G equivariant family. And if you get one thing from this talk, I want you to appreciate this definition. So the family means that for every point on the sphere, we have an invertible TQFT. Or more generally, we can just have any theory. Now, if this was a symmetric family, we would say that we want all these theories to have a G symmetry. And in fact, that G symmetry, these are all models happening in the same Hilbert space. We want G to act on that Hilbert space in a way that gives you the G symmetry of every one of these theories. For G equivariant theory, we want almost the same thing. We want a G action on Hilbert space so that if you act on the Hamiltonian, say, at this point, that it takes you to the corresponding point on the sphere that the group acts on the sphere, and this action on the underlying Hilbert space induces that action on the sphere. So if you like, this G is acting like a duality group on this family. So for instance, you could think about any number of examples. So like in our time reversal, in our T breaking case, V was the sign, or 2 plus 1D. Irona V is the sign, SV, S0 is 2 points. Here we had the theory with some M0, and here we have the theory with minus M0, and time reversal symmetry exchanges them. So this is a T equivariant family rather than a T symmetric family. And this defines a map called the residual family anomaly. It goes from our bulk anomalies, which were this type, and it goes to some kind of equivariant homology. So what you can think of is that these are invertible TQFTs. They're equipped with their partition functions that you can evaluate on a space-time with a G gauge field and with some structure, which is just what we had before. But the extra thing is some phi, where phi is a section of this associated bundle. Now we take the associated bundle, we take the gauge bundle, we take the G product with the sphere. So phi is a section of this bundle. And if you like this residual family anomaly map on these spacetimes, what it does is you just forget phi. So this map is defined by just setting phi to be 0 or some constant, say, or not setting to be constant, but like just forgetting it in the data. So yeah, I don't have time to really illustrate this, but the proposition is that the image of the defect anomaly is the kernel of this residual family anomaly. So this residual family anomaly is exactly the obstruction to having a local V defect. So yeah, in our paper, you can find many interesting examples of this. We can also understand the kernel. Let's see here. So the kernel of the defect anomaly map, these are anomalous V defects occurring in anomaly-free theories. So let me say that when we have these equivariant families, even if we have a unique gap ground state at every point, it doesn't mean that the G symmetry can be gauged in the sense that we need in order to define such a partition function. You couple to a gauge field and a section. So they can be anomalous. An example of that is the SO3 action on the spin half in a magnetic field. So there you have a unique ground state on the sphere, but there's a sort of projective representation at the origin can be reconstructed by the anomaly of that equivariant family, even though it's an invertible family. So, but here I'm talking about anomaly-free theories. So anomaly-free equivariant families. So there's a map, it's an index map, which takes a family, say in D-1 dimensions, because we're thinking about having an invertible, twisting by some invertible family on the boundary of type GS eta. It lives over the sphere. And what this is going to give us is some defect anomaly, GS eta plus V. And if you like, this map is sort of compactifying the TQFT on the sphere. So for example, in the 2+1D Majorana, remember this defect anomaly map, Z8 plus Z to Z16 was given by AB to B minus 2A. So there's a kernel, evidently. Is generated by, what's it generated by? I don't know. 1, 2, it looks like. B is 2 minus 2a. Okay, it looks good. So let's see that that's the image of the index map. And now the index map, it goes from b minus 1 is 3 here. So we have z2 spin. These are time reversing z2s. So it's sort of pin plus all this data and plus, but now equivariant for S0. And turns out that this is a Z. And so we want to compute map into Z8 plus Z and show that it gives us this kernel. Now the generator, it's a family over S0. So we have to pick 2 theories. And the theories to pick, at this point, you pick 3D theory. So here we have a P plus IP. Here you have P minus IP. Now I chose plus and minus so that the family could be T equivariant. So T changes the P plus IP to the B minus IP. So you get a T equivariant family over S0 here. In order to compute the index map, what you do is you look at the essentially the V defect associated with this family. So what you do is you go around the sphere, which in this case means that you put the P plus IP on this side, P minus IP on this side. And we're going to look at what we get on the interface. Okay, so each of these has a chiral mode on the edge, but they have modes of opposite chirality, but there's another opposite because they're on opposite sides of the wall. So you get 2 modes of the same chirality. Okay, but now we need to see how we need a unitary Z2 symmetry acting here. So we need to see what that is. So that's going to be time reversal times CRT, right? So if we do time reversal, what it does is it changes P plus IP, P minus IP, both these modes flip direction. But then when we apply CRT, what happens is we do time reversal, so they flip back, and then we do reflection, so they swap. So T times CRT is a swapping symmetry. And so this has eigenvalues plus or minus 1. So we have 2 chiral modes, one of which is charged, one of which is neutral. So what do we have here? 2 chiral modes, one of which is charged. So it gives the kernel, as we hoped. Okay, so the full picture, just draw sort of what we're talking about here. The last proposition is that the kernel of the index map is the image of this residual family map. So all these maps fit together in a really nice structure, which looks like this. So the defect anomaly map, just to recap, so the defect anomaly map allows you to reconstruct the bulk anomaly from the defect anomaly. So you have the bulk anomaly here in the middle and the defect anomaly on the left. The residual family anomaly gives the obstruction to being able to do this, which is valued in a kind of family anomaly world. And meanwhile, we have the index map that gives the ambiguity, and I'll draw this guy up here because it's the same group, but just with a dimension shift. So the index map comes around here, and its image is the kernel of the defect map. And things just keep going. G minus K plus 1, GS eta plus V. You have another index map coming around here. And so this continues forever in the long exact sequence. So for a given G and theory type S and twist eta and some representation, you get correspondence between these anomaly matching problems in all dimensions. They fit together to this long exact sequence, which turns out to be like a really computable thing because of the exactness most of these maps are usually determined. So there's lots of examples that we computed in the paper that took no effort at all. And yeah, I recommend you look at them because there's a lot of interesting, like, non-trivial physics contained in these maps, especially in this index map, things about like Majorana modes at the centers of vortices and superconductors and stuff like that we love, all come out because of exactness of these maps. So yeah, let me end there, and thank you for your time and attention.
So thank you very much. Are there any questions?
Question. Is there a way to interpret this as coming from some sort of short exact sequence?
Say again, I didn't quite hear.
Is there a way to interpret this long exact sequence for anomaly matching as coming from some sort of short exact sequence, like that induces a long exact sequence?
You're saying like in cohomology or something like that?
Yeah, like you somehow take, like, applying a functor that computes the anomaly in some sense.
I don't, well, there is a, we have constructions of this guy as like a co-fiber long exact sequence. So it comes from a very general thing in homotopy theory, but I think it's more than, it's more like a co-fibration rather than a short exact sequence. But yeah, it does have an origin like that.
Thank you.
Yeah, sorry if I can interrupt. So you're right. If you do ordinary cohomology, then it comes from a short exact sequence of chain complex. But for these more generalized cohomology theories, the right context in algebraic topology is called spectra. And the notion of short exact sequence of chain complex gets replaced with what we call fiber sequence or co-fiber sequence. And we also do that in the paper.
Mm-hmm. Yeah, thanks. Exactly.
So it seems there are no more questions. Let's thank Ryan again, and can we